So it's a pleasure to introduce Pedro Riul. He's professor in Universidade Federal de São João del Rei, and he will talk about curvature loci of three manifolds in Euclidean space. So thank you very much, Pedro, for accepting our invitation, and you can start now, please.
Thank you very much. Thank you for the very kind invitation. Always a pleasure to be in São Carlos, if not in person, at least online. I will talk about the curvature loci of three manifolds in Euclidean spaces. Here are the contents. And the objects of my study are regular three manifolds in R6, which will be denoted like this, M3 reg, and also singular co-rank 1 three manifolds in R5, which will be denoted like that. First, some background. We will start with regular three manifolds in R6. This will denote, as I said, the three manifold in R6. F will be local parametrization of the tree manifold. Since the manifold is regular, for each point P, we have a tangent space, a three-dimensional tangent space, and a three-dimensional normal space. We can define the second fundamental form in a very simple way by projecting orthogonally into the normal space the derivative of second order of the parametrization F, as we do for regular surfaces in R3, for example. Well, the curvature locus of a tree manifold is the image of the unit tangent vectors via the second fundamental form. It was first defined by Little for regular surfaces, but we can also define it for singular objects and also for tree manifolds. Well, taking spherical coordinates, we can parameterize the curvature locus like this. It was shown by Rosane Binotto, Sueli Costa, and Carmen Romero Fuster in 2016. And this is the local parametrization of the curvature locus. We have the first normal vector space at the point P, the affine hole of the curvature locus. EP is a linear subspace of the first normal vector space, which is parallel to the affine. And we say that a point is of type Mi if the dimension of the first normal space is I. This is also equivalent to say that the second fundamental form has rank I at the point B. And the authors, they showed that if the dimension of the first normal space is 3, the curvature locus has one of the following designs: a Roman-Steiner surface, a cross-cap surface, a Steiner type 5 surface, or a cross-cup, which will also be called as type 6. These are the substantial curvature loci, which means that they are non-planar. There are also two other, the truncated cone and an ellipsoid. But they can also be planar, one of the 6 possibilities. So we have other possibilities. This is the case when the curvature locus is planar. Daniel Dreibelbis in 2012, he showed that if we take a basis of the tangent space and a basis for the normal space, he defined for any vector, any tangent vector u, this 3 by 3 matrix in the following way. And we say that this tangent direction u is an asymptotic direction if the determinant of this matrix vanishes. Very well, that's what we need for regular tree manifolds, I'm sorry. Now, singular tree manifolds in R5. To construct Core 1 singular tree manifold in R5, I will use this construction. This construction was first given by Luciana Martins and Juan Ballesteros in 2015 when they studied Core 1 surfaces in R3. Also for Core 1 surfaces in R4, Cidinha, Raul, and myself did it for surfaces in R4, Core 1 surfaces in R4. So the construction goes like this. We take a regular tree manifold, M tilde, a local chart of this tree manifold. G is a Core 1 map, so we will take a point Q at the regular tree manifold, and the singular point in the singular tree manifold will be the image of Q via this map, this Core 1 map G. And we can take a local parameterization at the singular point P by this composition. Well, by doing so, we have the tangent space. Since the tree manifold is singular, the tangent space here is two-dimensional, and the normal space is three-dimensional. What happens is, since we are interested in the second-order geometry of the tree manifold, this tangent space, two-dimensional tangent space, it doesn't help us much. So what happens is, we will borrow the tangent space of the regular tree manifold. So this tangent space here, it will act as a tangent space at the singular point for the Core 1 tree manifold in R5. So this is the space that we will use to define the first and second fundamental forms, the ingredients that we need for the singular tree manifold. First, we start with the first fundamental form, defined this way. This is not a Riemannian metric, it's a pseudometric instead, since the map G has Core 1. And taking a basis for the tangent space, we can write the coefficients of the first fundamental form in a very straightforward way. And taking a tangent vector U, written as a linear combination of the bases, we can write the first fundamental form in a pair U using the coefficients of the first fundamental form. The second fundamental form is defined in a basis also of the tangent space, and then we can extend the second fundamental form to the whole space in a unique way as a symmetric bilinear map. The second fundamental form doesn't depend on the choice of the local coordinates of the regular tree manifold. And taking a normal direction, we can write the second fundamental form along this direction by taking the inner product. And we can write the coefficients of the second fundamental form along this direction, taking local coordinates. So we have the coefficients of the second fundamental form. And fixing an orthonormal frame for the normal space and tangent vector U, the quadratic form associated to the second fundamental form, we can write it like this, using the coefficients of the second fundamental form. Very well. Now, we are ready to define the curvature locus for a singular tree manifold in R5. This is done in the same way as we did for regular tree manifolds. So the curvature locus will be the image via the second fundamental form of the unit tangent vectors What happens is, well, this is how we denote the curvature locus. And what happens is, for a regular tree manifold, the subset of unit tangent vectors is a sphere. In this case, however, since the first fundamental form is not a metric, but a pseudometric, it messes up a little bit the subset of unit vectors. Now, the subset of unit tangent vectors is a cylinder, is a unit cylinder, which we will call CQ. And we can parameterize the curvature locus using the coefficients of the second fundamental form. Well, one might ask, well, as I said, this construction, these definitions, they were first given by Luciana and Juanjo, and then for singular surfaces in R4 by Cidinha, Raul, and myself. Here we have some examples of curvature loci. We can have a parabolic region, a plane, a half line, a line, a point, a paraboloid. These are some examples, but we have some more interesting examples as well. For instance, for this parametrization F, this is the curvature locus at the origin. It's a singular surface, or we can have something like this, maybe, or even this one. Looks like a heart or something. Very well. For singular trimanifolds, we also have the minimal affine space, containing the trimanifold. We have EP as the lowest dimension vector space, parallel to the affine. We will also say that a point is of type My if the second fundamental form has rank I at B. And we will define this matrix alpha, given a local parametrization of the trimanifold. And we will say that the point P is a non-degenerate point if the determinant of this matrix isn't zero. We will denote by A2 the space of two jets of diffeomorphisms acting at source and target. J235, the subspace of two jets from R3 to R5. And sigma 1 is the subset of corank 1 two jets. What happens is we were able to obtain the orbits in the subset of corank 1 two jets under the action of A2, and we have 6 orbits. This is also very similar to what was done for surfaces. And here we have conditions over the coefficients of a complete two-jet for the A2 classifications. So the only case where the point P is non-degenerate is in the first orbit, and we have the conditions over the coefficients in this table. What happens is, when we are studying surfaces, corank 1 surfaces in R3 and R4, this A2 classification distinguishes completely the affine class of the curvature parabola. For surfaces, the curvature locus is called the curvature parabola. And now, does it do the same job? Well, it doesn't. For instance, we have these two maps. They are A2 equivalent, but the curvature loci, they do not belong to the same affine class. This first one is a paraboloid, and this one was the first singular one that we saw in the examples. Well, so this classification doesn't work so good for us in general. However, we have a more specific result that if the parametrization F is given like this, that means we don't have x squared, xy, or y squared. Then in this case, for this particular case, then the A2 classification distinguishes, in a way, the affine class of the curvature locus. In the first orbit, we have a substantium surface, then a planar region, a plane, a half line, a line, and finally a point. But this is a very specific parameterization. R2 is the group of two jets of diffeomorphisms from R3 to R3. O5, the group of linear isometries. And this subgroup of A2, it acts also on the subset of Courant 1 two jets. And we showed that if we have two Courant 1 tree manifolds in R5, locally parameterized by Fm, Fs, then the two jets, they are equivalent under the action of this subgroup if and only if there is a linear isometry between the normal spaces that maps one curvature locus to another. But, well, we're still far from understanding how the curvature loci, how they work. Well, to get a better understanding, we will use nets of quadrics. The thing is, one can study the affine geometry of the second fundamental form by studying the G invariants of the action in the space of quadratic polynomial maps from R3 to R3. That means the second fundamental forms. And each such mapping, it generates a system of quadrics which are denominated by net of quadrics. This is a well-studied object by Duplessis and Wall. In many papers, I put two of them here, also in the book. H23 is the space of homogeneous polynomials of degree 2 in three variables. And what is a net, actually? Is a system generated by three polynomials. So, as we see here. So it's a system of three polynomials, each one of them in H23. And the way we relate them to the second order geometry is like this. Given a net, we can associate it, the two jets of parametrization of a Courant 1 tree manifold in R5, and also its lifted smooth tree manifold of regular tree manifold in R6 in this way. And given a net, we can write local parametrization for both the singular tree manifold and the regular tree manifold in this way. By doing this, the second fundamental form for these tree manifolds, they are at the origin given by the quadratic map Q. That means the net. A natural question is, if we have two G equivalent nets, what happens to the curvature? What happened to the curvature loci of them? Do they have the same affine equivalence class? Well, no. No, they don't. We wish. What happens is, if we take, for instance, a tree manifold parameterized by this map F, at the origin, its curvature locus is a Roman-Steiner surface. And its associated net is G equivalent to this one. And taking changes of coordinates in the source, we can show that this one is also G equivalent to the last one, to this last one. And if we take the tree manifold, whose second fundamental form is this one, the curvature locus at the origin is a Steiner surface of type 5, which means the curvature loci, they are not affine equivalent. For Courant 1 tree manifolds in R5, singular Courant 1, at a non-degenerate point, that means that the determinant of the matrix alpha that I defined previously is different than 0, we have a pre-normal form for the classification of the nets. This is not a final answer, but this allows us to work further on results. So if we have a Courant 1 map from R3 to R5, P being the origin, a non-degenerate point, taking changes of coordinates in the target given by the action of the linear group, the associated net is equivalent to this GP, where A, B, and C, they are all non-zero, and P is equivalent to the one of the following normal forms. And also, furthermore, if 2, P and Q, they are GL2 times GL3 equivalent, then we can find a matrix B such that the nets, they are linear equivalent. This is not a final answer, but this will help us to continue this study. For instance, we can say that for a generic choice of A, B, and C, non-zero, the curvature locus of the lifted regular trimanifold in R6 with GP as in the previous result, the curvature locus is a Roman-Steiner surface. Well, but is that it? Is that all we got? What else? Well, we have been looking for some answers, and let's take a look. In 1996, Kaufman, Schwartz, and Stanton, they provided a projective classification of quadratically parameterizable surfaces. And Rosani, Sueli, and Carmin, using this classification, they provided a description of these surfaces, which are compact. And those are the possibilities for curvature loci of regular trimanifolds in R6. As we saw, the Roman-Steiner, the cross-cap type 5, type 6, the cross-cup, the truncated cone, and the ellipsoid. Very well, but what they did is they said, well, those are the possibilities. But what they didn't do is when we will find each one. That's what we try to do. Let's take a look at them. The Roman-Steiner surface, it has 6 cross-cap singularities, which we will call the CC points. They are joined in pairs by 3 transversal double point curves, and they all intersect at the triple point. This is a very well-known surface. Also well-known, the cross-cap. It has 2 cross-cap singularities, and they are joined by a transversal double point curve. The type 5, it has 2 cross-caps. They are joined by a transversal double point curve. One of these cross-caps, it lies on a tangent double point curve. And the tangency of this double point is non-degenerate. That means that the tangent sheets, they have different curvature. And the 2 endpoints of this curve is a non-finitely determined singularities. And those points, these 2 endpoints, we will call them the TCC points. So it's like a T shape, the 2 cross-caps joined here by the double point curve, and those 2 other singular points, which are non-finitely determined, joined by this other curve. The type 6, it has no cross-caps. It has a tangent double point curve where the tangency now is degenerate. That means that tangent sheets, they have the same curvature. And the 2 endpoints of this curvature are, again, not finitely determined singularities. And we call these 2 endpoints the DTCC points. Besides, we have the truncated cone. It's a compact cone. We have a singular curve of singular points corresponding to the base of the cone, and a singular point corresponding to the vertex of the cone. None of them are finitely determined. And the ellipsoid, it has a curve of non-finitely determined singularity, singular points as well. Well, we will try to obtain a classification studying the second fundamental form by studying it we want to be able to say what curvature locus we will get for that second fundamental form at a point P. To do so, we will proceed like this. We already know that the curvature locus is the image of the unit tangent vectors via the second fundamental form. We can take the unit sphere as the inverse image of this map in a very natural way. We will take a local parametrization in a Monge form for the tree manifold, the regular tree manifold, and find matrix MF, this 4 by 3 matrix. Very good. Here we have the two jets, the derivatives of the two jets, and here the derivatives of this map, which gives the unit sphere. Now what? Well, the zeros of the 3 by 3 minors, we have 4 3 by 3. This is a 4 by 3 matrix. We have 4 3 by 3 minors in this matrix, MF. And the zeros of them, they are the solutions to a system of 4 homogeneous polynomials of degree 3 in 3 variables. So we have 4 ternary cubics. And those solutions, each one of them is a homogeneous algebraic variety, which is generically a collection of lines passing through the origin. And each of them have a certain multiplicity, and this multiplicity is given by the number of points of the intersection of the line with a generic plane away from the origin. So the intersection of these lines with the unit spheres, they correspond to the singularities of the curvature locus. So we did a classification of the singular points of each possible curvature locus. And now we are able to study these singularities. How come? Using this characterization. Suppose that we have a regular tree manifold in R6, parameterized by f in the Monge form, and we will work only with the substantial curvature loci, which means, again, that they are not contained in a plane. So we have this characterization. The curvature locus will be a Riemann-Steiner if and only if the zeros are the subset of zeros is 6 real lines with of multiplicity 1, each of them. We have a cross-cap if and only if we have 2 real lines and 4 complex lines of multiplicity 1, and so on, so on, so on. So we were capable of providing this characterization of the curvature locus looking to the zeros of that matrix. So we have all the possibilities we can distinguish between them. What happens is here at the truncated cone and the ellipsoid, we can also have planes as solutions. Very good. Let's look to examples. We have this second fundamental form for a regular tree manifold at the origin. Those are the 3 by 3 minors of the matrix. We can find the solutions. We have 4 lines here. For instance, to evaluate the multiplicity of the last one, for example, we take a plane, the plane z equals to 1, which is transverse to the line, which is just the z-axis. And we compute the dimension of this algebra by replacing z by 1 and evaluating x and y at 0, 0. Then we get multiplicity 1. What happens is the first 2 solutions, those one, they have multiplicity 2, and they correspond to TCC points. And the last 2, they are cross-caps. They correspond to cross-cap points. So in this case, the curvature locus is a type 5 surface. Another example, Again, a second fundamental form at the origin. We have the minors, the 4 3x3 minors. Here we have only two solutions, two lines. Both of them have multiplicity 3, so they correspond to DTCC points, which means that the curvature locus is a type 6 surface. And there is a natural equivalence when we work with determinantal matrices. This group, G bar, where R is the change of coordinates in the source and H is this product of linear groups, this group, it acts naturally by multiplication to the left and to the right, acts on the 4x3 matrices in a way that if two matrices, they are G bar equivalent, then the subset of zeros, they are isomorphic. Well, sounds good, but what happens is, inside a certain G orbit, the curvature locus doesn't change, because since the curvature locus are given by these subsets and they are isomorphic, well, inside a certain G bar orbit, we have the same curvature locus, curvature loci. Okay, but if we take two parametrizations of regular tree manifolds whose associated matrices are G bar equivalent, we may have associated nets in different affine G orbits. So the curvature loci, they are isomorphic, but the associated nets, they are in different affine G orbits. For instance, if we take these two, G1 and D2 as the second fundamental forms at the origin, the curvature loci of both of them is a truncated are truncated cones, but the associated nets, they do not belong to the same orbit. Okay, we have some answers for regular tree manifolds, but what about courant 1 tree manifolds in R5? Can we apply the same method to study the curvature loci for this case? We can. What happens is, if we project orthogonally a regular tree manifold in R6 along a tangent direction, we will get singularity. In particular, we will get a singular tree manifold in R5. The regular and the singular tree manifold, they have the same fundamental form. So it's natural to try to apply the same method here. The difference is, for the regular case, the curvature locus is the image of a unit sphere, and for the singular case is the image of a cylinder. So applying those differences, let's take a look to some examples. Take this G as the second fundamental form of a regular tree manifold in R6 at the origin. By doing the calculations, we can see that the curvature locus at the origin is a Roman-Steiner surface. Since the subset of zeros of the minors is composed by 6 real lines. Okay. If we project this regular tree manifold along this direction, which is an asymptotic direction of the regular tree manifold, and the image of this asymptotic direction is the triple point in the Roman-Steiner surface. If it is the triple point, it cannot be a cross-cut point. The curvature locus of the singular tree manifold, it will have two cross-cut points. Also, there are three solutions in the set of zeros. Here, this is the matrix. Doing the same thing as we did for regular manifolds, we can do for singular, just replacing the sphere by the cylinder. So we have two cross-cut points, one being the z-axis, the direction that we projected. the node tangent, which will be the node tangent direction, the direction that lies inside the cylinder. If we project along another direction, the y-axis, which is an asymptotic direction whose image is a crosscap, then the curvature locus at the origin is a surface with 5 crosscap points. So we have different behaviors here depending on which direction we project. Here, the first image is the curvature locus of the singular manifold, projecting along the first direction, the z, and here is the one with 5 crosscaps. Okay, another example. Taking now this G as the second fundamental form at the origin for a regular trimanifold in R6. Again, the curvature locus is a Roman-Steiner, but this time the z-axis is not asymptotic, is not an asymptotic direction. If we project along the z-axis, the curvature locus at the origin of the singular trimanifold still has 6 crosscaps, so we didn't lose any of them. But if we project along this other direction, whose image is the triple point of the curvature locus, the curvature locus of the singular trimanifold at the origin has 4 crosscaps, so we lost 2 of them. Okay, so what's going on? Well, it depends. If we have a regular trimanifold in R6, and its projection, a singular trimanifold in R5 along a tangent direction, if the direction we are projecting is not asymptotic, then these two zero sets, they are isomorphic. Since they are isomorphic, in particular, the curvature loci of the regular and the singular trimanifolds, they have the same number and type of singularities. However, if we are projecting along an asymptotic direction, then the curvature locus of the singular manifold has at least 1 singularity less than the locus of the regular manifold. As we saw in the examples, if we project along an asymptotic direction, we lose crosscap points. And in particular, if the direction of projection corresponds to a crosscap singularity, this crosscap goes to infinity in the locus of the singular manifold. So we, in this work, joint work with Raul and Cidinha, we were able to study, to give a more deep study, let's say, of the curvature loci, both of regular and singular trimanifolds in R5. And that's it. Thank you very much.